Hi everyone. In this lecture, we will talk about mathematical expectation, and which is an important concept in probability theory. And it is always good to learn about this concept because in programming also you might be facing some problems which are related with calculating the expectation of something. Okay, so let us talk about what is this term expectation. So expectation is kind of a weighted average value of a random variable. Now you may ask, what is a random variable? Okay, so a random variable is one of the outcomes of a phenomena or a random event, you can say. Okay, the random variable is one of the outcomes of an experiment. Okay, so now you may ask, what is a experiment? So let us denote, let's take few examples of a random experiment. For example, you throw a coin. Okay, you throw a coin in the air, and that coin may get a head or a tail as an outcome. Okay, so we can say x is a random variable that can take the value head, or it can take the value tail. Okay, or maybe another example could be you throw a dice, and this is a dice with 6 sides, and you can get the numbers in the range, let's say 1 to 6. Okay, so x is a random variable that can take the values 1, 2, 3, 4, 5, and 6. Okay, now I hope you understood uh, what is a random variable. So what is the expectation? So we'll calculate what is the expected value if you throw a dice. Okay, so it's kind of a weighted average. So we'll see how we can calculate this average. So mathematically, for a discrete variable x. Okay, so now let me also talk about the difference between a discrete and a continuous variable. Okay, so random variables come in two flavors. They can have discrete values, or they can have continuous values. Okay, for example, let's say x is a random variable that denotes what would be the temperature of today. Okay, so the temperature for today is a cold day, so maybe I can say the temperature is around 10 degrees Celsius. Okay, but it can be 10.1, it can be 10.2, it can be 10.25. Okay, so now you can see x denotes the variable temperature for the day, and it is a random variable, and it can take continuous values. Okay, it can take continuous values. So we will say x is a continuous random variable, whereas in case of throwing a die, x can take only one of the fixed values. Okay, so one of the n values in the range 1 to 6. In this case, we say it is a discrete random variable because the outcomes have discrete values. Okay, the outcomes have discrete values. So I hope you understood the difference between a continuous and a discrete random variable. Most of the problems that we would be discussing, they would be based upon the concept of discrete random variables. Okay, so mathematically, for a discrete random variable x with the probability function p of x, the expected value, it is denoted using e of x, is given by summation of xi into p of xi. So where p stands for the probability of that particular value, the summation runs over all distinct values of xi the variable can take. Okay, so basically, if I have something like x, what is the possible values of xi? So x can take the value 0. Sorry, in case of a die, okay, it can take the value 1, it can take value 2, 3, 4, 5, and 6. So what is p of xi? So p of xi denotes what is the probability of each value of xi. Okay, so if this is the ith outcome, the probability that this die will throw 1 by 3. So assuming it is a fair die. Okay, assuming it is a fair die, like every side has an equal probability of showing up, so we can say this probability is nothing but 1 by 6, 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 and 1 by 6. So each of the side has an equal probability, and that is 1 by 6. Now how do we calculate the expected value that can show up on a die? So that is nothing but summation of xi into p of xi. Okay, that is nothing but 1 multiplied by 1 by 6 plus 2 multiplied by 1 by 6 plus 3 multiplied by 1 by 6 plus 4 into 1 by 6, 5 by 6 and 6 by 6. Okay, if you just find out this, it is nothing but 1 by 6 common, 1 plus 2 plus 3 plus 4 plus 5 plus 6. This sum is what? So this comes out to be 3.5. Okay, so now what you can see is 3.5 is the expected value. It's some kind of average value that you can expect when a die is rolled, let's say infinite number of times. Okay, so this is the expected value that you will get, and this is not equal to the most probable value. Okay, it is not equal to the most probable value. So expectation is not same as the most probable value, because on a die you can never get a value 3.5, but this is kind of an average. If you do a lot of experiments of rolling a die, the average would be close to this result. Okay, this is what you can expect in the long run, that your sum of values divided by the number of dice throws would be close to 3.5. So this is what an expectation is. Okay, so I hope you are able to understand what is the meaning of expectation. Let me also talk about for a continuous variable with the probability density function p of x. Since a variable is like it's continuous, let's say the variable is like temperature, and here we say, okay, probability of having that particular temperature. Okay, so maybe it's a cold day, so the average temperature maybe is around 10. So maybe you might get this kind of a probability distribution curve. So in this case, the expected value of E of x, okay, or E of temperature is given by x px into dx. So basically you are doing this integration here. Okay, so it is integration of x px into dx. So this is nothing but this is again the area under the curve. So it's integration is also a way of summing up, but this is used for continuous variables. Okay, so it's more into the mathematical side. In programming, you might not be needing to implement this integration formula in your code. Okay, it's going to be very rare. Okay, but just to tell you that these two formulas are equivalent. Integration is like summation over a continuous variable, and the previous case that we just saw, this is a summation sign. It's for a discrete variable. This can be easily implemented using a for loop. You iterate over the values of x, you should know the values of p of x, and you can find out the expected value of a given variable. Okay, so that's all for this lecture, and thank you. Hi everyone, so in this lecture we are going to talk about an important theorem which is known as linearity of expectation. So basically it is a theorem that states that the expected value of the sum of two random variables, okay, it can be more also, two or more random variables, is equal to the sum of their individual expected values, their individual expected values. Okay, so now you may ask, let's try to make it more clear. Okay, so these random variables can be dependent or they can be independent as well. Okay, so it does not matter whether the two random variables are dependent or they're independent. Okay, so let me try to explain you with the help of an example. So this is how you state this mathematically, that E of x1 plus x2 is equal to E of x1 plus E of x2. Let us discuss one example. Suppose we are playing a game in which we take the sum of the numbers rolled on a two six-sided die. Okay, calculate the expected value of sum of the rolls. Now you're throwing two dice, so what are the possible outcomes? So you can see this matrix. Okay, so on the first die you get 1, on the second die you also get 1, so the sum is 2. On first die you get 1, on second die you get 2, the sum is 3, and so on. Okay, so you will have basically 6 into 6, you will have 36 outcomes. Okay, and the probability of each outcome, you know, it's going to be 1 by 36. Okay, and now if you want to find out what is the expected sum, on the 2 die. So you will be doing, okay, 1 by 6, 1 by 36 into 2 plus 1 by 36 into 3 plus 1 by 36 into 4. Okay, so all those sums you would be iterating upon. This you would be doing. Now the rule of linearity of expectation states that, so all the 36 moves you would be iterating upon. So this is the basic method that we are doing. Okay, so but if we try to solve it smartly, if you use the rule of linearity of expectation, that is going to basically say that this is nothing but equal to, so we can say, we want to find E of x1 plus x2. So it basically says that this expected value is same as the expected value from the first die plus the expected value from the second die. So if you see this we have already seen that this is 3.5, this is also 3.5. So we can finally say this sum is 7. So by using this principle, we are able to simplify this problem a lot. Instead of iterating over 36 possible cases, we broke down into these two values that we already know. And this is how rule of linearity of expectation is going to help us to simplify the problem statements. Okay, so you can see this is how powerful it is, and that's all. Hi everyone, so let us try to solve a problem using the rule of linearity of expectation. So let us go through this question. So it says a fair coin is thrown n times. What is the expected number of heads that you can get? Okay, so let us consider this experiment of flipping a coin n times, and let us denote the outcomes of the experiment using this array. So the first experiment outcome is, let's say, E1, the second experiment is E2, E3, and up to En. So we want to calculate E of Z, that is nothing but E of E1 plus E of E2 plus E3 plus up to En. So where E of I, what is E of I? So E of I denotes, it will take the value 1 if the ith experiment got the value head. Okay, in the ith experiment, if you got a head, this would be 1, or it would be 0 if you got a failure. Okay, let's say if you got a tail. So now what we can say is that this can be written as E of E1 plus E of E2 plus E of E3 and up to E of n. Now we want to find out what is the value of E of I. Okay, what is the expected value of the ith experiment? So we know that this can be written as sigma xi into pi, where xi is the value that you got. So xi is 1. What is the probability of getting a head? That is half. What is the probability of getting a tail? That is also half. Okay, so this comes out to be 0.5. So what we can do is we can put each of these values as 0.5. Okay, so you're basically doing summation of 0.5 how many times? N times. So this becomes n into 0.5, and this is equal to n by 2. And you can see that this is the probability. This is the probability of getting, this is the expected number of heads if you throw a fair coin n times. So basically it says half of them would be heads, and that is also seems true logically, because half the number of times you can expect heads. Okay, and I hope you understood this problem as well, and that's all for this video. Hi everyone, in this lecture we will discuss how we can approach some more problems involving the expectation. So let's go through our first question. So it says, what is the expected number of coin flips to get a head? So let's discuss the approach that we will follow to solve all problems of this kind. So we'll assume that this expected number is x, okay, and we want to calculate this x. So we have discussed that the expectation x, okay, so, or you can say E of x, whatever it is. So we want to calculate this value. So what we are going to say, this is equal to summation of xi into p of xi. This is what we have learned. Okay, so what is p of xi? It is the probability of getting an outcome xi. Okay, so what can be an outcome in this case? if you throw a coin, you can get a head, you can get a tail. So suppose if you get a head, okay, that means you got the success in the first throw itself. So how many throws you needed? You actually needed only one throw. So you needed only one throw, okay. And what is the probability of getting the head in the first throw? That is nothing but half, okay. But what if you don't get a head in the first throw? Suppose you get a tail, okay, let's say you get a tail. Now how many throws you would need to get a head, okay. So effectively you have already wasted one throw, and you are saying the expected number of throws to get a head is x. So effectively you would be needing x plus 1 number of throws, okay. This is an important thing you need to understand, that you have already wasted one throw, okay, and you did not get a head. Suppose you got a tail in the first throw, okay, that means you got a tail and you are expecting you will require x number of more throws to get a head. So the total number of throws would be 1 plus x. It would be 1 plus x into the probability of getting a failure in the first throw. That means the probability of getting a tail in the first throw, that is again half, okay. So this is equal to x. Let us solve this equation. So it becomes 2x equals 1 plus 1 plus x. So this becomes 2x minus x. This is equal to 2, and this gives us the final value of x, that is equal to 2. So yes, we can say we would require 2 number of throws to expect a head, and that makes sense, okay. That makes sense as well, okay. So this is how you will frame a kind of a recursive relation, and you will try to solve this equation to get the number of coin flips to get ahead, okay. So let us see one more example in the next lecture. Hi everyone, so let us move on to the next problem statement. So we have seen what is the expected number of throws to get ahead. So in this question we are slightly going to change the question. So the question is, what is the expected number of throws that you would need to get 2 consecutive heads, okay. So that means we want to get a head followed by a head again, okay. So now what may happen is, let us assume that our answer is equal to x. The expected number of coin flips is equal to x. Now suppose you throw a coin once and you end up getting a head, okay. So what would be the probability of getting a head? 1 by 2, okay. And suppose you again throw a coin, you again get a head. So what would be this probability? 1 by 2. So we actually throw a coin 2 times, and suppose we got a head and again a head. That would be equal to 1 by 2 into 1 by 2 multiplied with 2. What could be the other case? Suppose on the first throw you get a head, on the second throw you get a tail, okay. So what would be this probability? Half, and again it would be half. That means now you have wasted 2 throws, and you would require x number of more throws to expect 2 more heads, okay. So that means in total you would require x plus 2 throws in this case. So it would be 1 by 2 into 1 by 2 into the number of throws, that is equal to x plus 2. What may happen in other case as well? Suppose you throw a coin and you get a tail in the first throw. In this case, what you will say? You will say, okay, I will try my experiment again and I will require x number of more throws to get 2 heads, okay. So in this case you have wasted one throw, okay. So you can say 1 by 2 into x plus 1. Any other case? No, we have already covered all the cases. So let's see how we can solve this equation. So it becomes x equals to, this 2 goes off, it is equal to half plus 1 by 4 into x plus 2 into again half into x plus 1. So let us multiply everything with 4. It becomes 4x, it becomes 4, it becomes 4, and it also becomes 4, okay. So this becomes 2, this goes off, and this becomes 2. So let us expand. So 4x equals 2 plus x plus 2 plus 2x plus 2. So effectively it becomes 2 plus 2 plus 2, 6, and this is x plus 2x, 3x. So 4x minus 3x is equal to 6. That means x is equal to 6. Okay, so that this is how you can solve this equation. And what we are saying is we can expect two consecutive heads if we throw a coin 6 times. Okay, so I hope you understood this problem as well, and see you in the next video. Hi everyone. So let us increase the complexity of the question a little bit, and instead of saying two consecutive heads or three consecutive heads, we are going to write for this general case what is the expected number of coin flips that are needed to get n consecutive heads. Okay, so the answer will obviously depend upon the value of n, so we need to generalize this and find our answer. Okay, so let's see how we can solve this problem. So let us assume that our answer is equal to x, and we throw a coin, and suppose we get a failure in the first throw. Okay, so the probability of getting a tail is 1 by 2, and we would require x more throws to get n consecutive heads. Okay, so it would be half multiplied with x plus 1, because we have already wasted one throw. So this is one case. Another case could be that in the first throw we get a head. Okay, the probability is half, but in the next throw we don't get a head. So suppose we get a tail, so that means we have wasted two throws and we would require x more throws. Okay, so in total we would be needing x plus 2 throws. So we can say, okay, it is 1 by 2 into 1 by 2 into x plus 2. Similarly, we get a head, and now we get a failure, we get a tail. So the probability is 1 by 8 into x more throws, so it becomes x plus 3. So I can say 1 upon 1 divided by 2 power 3, it is x plus 3. Okay, similarly it will keep on going. In the worst case, what is going to happen, we are going to say that suppose we get n minus 1 heads. Okay, and the nth experiment gave us a tail. Okay, in this case what is going to happen, again it would be 1 divided by 2 raised to the power n. That means we have wasted n number of throws, and we have to do the experiment again, which would expect x number of tries. So it would be x plus n. So we can say plus 1 by 2 raised to the power n into x plus n. All right, then there would be a case in which we get a success. Suppose in all the n throws we get heads. What is the probability of this happening? So it would be 1 by 2 raised to the power n into how many trials we needed. We actually needed n number of trials. Okay, so that would be n. So it would be plus 1 by 2 raised to the power n into n. Okay, so this is the case where we get all the n heads in n number of tries. Okay, so that this is where we just get a success, but otherwise even if there is one failure, then this would be the series that we would be getting. Okay, now let us try to simplify this, how we can solve this equation. So we can say x equals what, if I take x common out of all the terms, it would be like x into 1 by 2 plus 1 by 4 plus 1 by 8 up to 1 by 2 raised to the power n. Okay, plus what, these terms, 1 by 2 into this, 1 by 4 into this, 1 by 8 into this. So it would be plus 1 by 2 plus 2 by 4 plus 3 by 8 plus 4 by 16 and so on, plus divided by n into raised to power n plus this term. So this term will carry come as it is, n divided by 2 raised to the power n. Now you may ask, how do we solve this equation? Okay, so if you now look carefully, this equation that we are looking here, this equation is a geometric progression. Okay, it's a GP, so you know how to find the sum of n terms of GP. It can be done. What about this? So in the denominator, this is GP. In the numerator, this is AP. And this kind of a series is called as AGP. Okay. So what you need to do? You need to find out the sum of n terms of a arithmetic geometric progression. That is again doable. That can be done. And this term is a single term, and this you can handle separately. Okay, so I'm not going to solve this GP and AGP for you. I'm just going to write down the result. So if you solve this equation, if you simplify, then what you are going to get? You're going to get the value of x as 2 raised to the power n plus 1 minus 2. This is doable. Okay, this is the final result that you would be getting, and you can verify. If you put n equal to 2, then in the previous example, for 2 consecutive heads we got an answer as 8, so it becomes 2 plus 1 minus 2, that is 8 minus 2, that is 6. So yes, we derived this answer 6 in the previous example as well, and that's so this is the correct result. We have not solved AGP for you, we have not solved GP for you. So if you go back to your school level maths or class 12th maths, I think, then you should be able to definitely able to derive this result. Okay, otherwise you can just skip and go to the next problems as well. Okay, so that's all for this video, and thanks a lot. Hi everyone, in this lecture we'll talk about Bernoulli's trial. So what is a Bernoulli's trial? So an experiment is called a Bernoulli's trial if it has exactly two outcomes. For example, an experiment may end up in a success state or it may end up in a failure state. Okay, so exactly two outcomes, and out of which one is desired. For example, flipping a coin, exactly two outcomes, a head and a tail. Okay, selecting a number from 1 to 100 to get a prime or not prime. So again, two outcomes, prime or not prime. Or rolling a die to get a 4. So exactly two outcomes, getting a 4, getting a non 4. Okay, so these all are examples of a Bernoulli's trial, and an experiment is a Bernoulli's trial if the outcome can be represented using yes, no, or a success failure kind of a state. Okay, so this is what a Bernoulli trial is in simple terms, and let's see at a theorem that is associated with Bernoulli's trial. So if the probability of getting a success in Bernoulli's trial is P, then the expected number of trials to get success is 1 by P. So effectively what we are saying is, if we need if the probability of success is P, then the number of trials we would need is 1 by P. Let us look at one example. For example, what is the number of trials you would need to get ahead? Okay, so the probability of getting ahead is what? If a fair coin is thrown, it is 1 by 2. Okay, and what is the number of trials you would need to get ahead? So it would be nothing but x would be equal to 1 by P. So 1 upon what is P? It is 0.5. So it is equal to 2. So you can say in 2 throws you can expect ahead. Okay, and what was the other method that we have already seen? By making a simple equation, so we can say we can say x is the number of trials. So if we get in the head in the first throw itself, it is 1 by 2 into 1. Okay, probability of getting ahead into number of throws. Or if we get a failure in the first throw, okay, that would be 1 by 2 getting a failure. And how many throws we would need? It would be 1 plus x. So again, if you solve this equation, it is equal to 2x plus 1 plus 1 plus x. So this becomes x equal to 2. So again, using this method, or if you use this method, you're getting the same answer. So you can use either of these, but this is more like a shortcut. You can get the answer for events which are Bernoulli trial in just one step. Okay, or otherwise you can use the basic equation method that we have already discussed. So this is theorem 1, and theorem 2 says the probability of getting success in a Bernoulli trial is P, then the expected number of successes in n trials is n by P. Okay, so for example, if you conduct multiple trials T1, T2, T3, okay, T4 up to Tn, so in any trial, if you are able to get success with a probability P, Then in n trials, how many successes you would have? Again, it would be p. You are going to add all of them, okay, and this would be nothing but n multiplied with p. So this is equal to np. As simple as that, okay. So these are the two theorems that you should be knowing, and from the next video we'll solve one problem on Bernoulli's trial. Okay, let us discuss this problem. Choose number. So it says n students are asked to choose a number from 1 to 100. Okay, what is the expected number of students that would choose a single digit number? So let us talk about a single student. Okay, what is the probability of single student choosing a one digit number? Okay, so between 1 to 100 we have only 9 numbers, so that means this probability would be 9 by 100. Now we are doing this experiment not for a single student, we are doing this experiment for n number of students. Okay, so if the probability of getting success in a single experiment is p, okay, then we have seen from theorem 2 that for n experiments or for n students, this is going to be n into p. Okay, so we can say this is going to be 9p upon 100, and that's it, that's the answer. Okay, this is nothing but a simple application of theorem 2 of Bernoulli's trial that we have seen in the concept video. Okay, so that's all. Hi everyone, so let us discuss this question of interviewing candidates. So it says candidates are appearing for interview one after another. The probability of each candidate getting selected is 0.16. What is the expected number of candidates you would need to interview to make sure you at least select somebody? So that basically means what is the probability of getting a success in an interview? Okay, in how many trials a candidate would become successful? That's another way of framing this problem statement. If you use the concept of a Bernoulli's trial, is this event a Bernoulli trial? The answer is yes. So either a person can pass in the interview or it can fail in the interview. Okay, so there are only two outcomes. So the probability of getting a success is 0.16. So how many trials you would need? That is nothing but 1 by p, and this is equal to 6.25. So you can say in 7 interviews, okay, you can round it off to 7. You can say in 7 interviews, you can say you will select someone. Okay, you cannot take 6.25 interviews, you have to take 7 interviews only. Okay, so you can say in 7 interviews you are going to select someone. Okay, and if you want to solve this using the equation method, you can still do it. So you can say x equals 0.16. If the person gets successful in the first interview, then, or if the person fails in the first interview, then you would require x plus 1 more interviews. Okay, so the probability of getting a failure, that would be 1 minus 0.16 into x plus 1. Okay, you can simply solve this equation, and again what you will get x equals 1 upon 0.16. This is again 6.25. okay, so this is method 1, which is using Bernoulli trial, and this is our standard equation approach that we have already seen. So that's all for this video. Thanks a lot. Hi everyone, in this lecture we are going to talk about a general type of problem which is known as coupon collector problem. Let us understand this problem statement, and this can be applied in questions of this particular type. Okay, so let's see this question. A certain brand distributes a coupon in a packet of chips. The coupon is chosen randomly from a set of n distinct coupons. So you have n type of coupons. Let's say coupon of type 1, coupon of type 2, up to coupon of type n. And any packet of chips can contain a coupon with a value x. Okay, I don't know what is this value x. So what is the expected number of packets that you will buy so that you get all the n distinct coupons? Okay, so you want to collect all n distinct coupons, and what is the number of packets you have to buy? That is what you need to find out. Okay, so another way to frame this question could be, how many throws are needed so that you see all the n faces of a n-sided die? Okay, so how many throws are needed to get all n faces of a n-sided die? Okay, for example, if the die has 6 sides, in how many throws you will see all the faces from 1 to 6. Okay, that is another way of framing this particular problem. Now let us discuss how we can solve this problem. So what we will do, it's okay, let us say that E of xi denotes the number of packets you will buy, denotes the number of packs you will buy to grab the ith new coupon. The ith new coupon. Okay, I'm not saying the ith coupon, I'm saying the ith new coupon. That means you have already collected I minus 1 type of coupons, and now you're collecting the ith type of coupon. And what is the value that we want to compute? We want to compute E of x. That means we want to get all types of coupons, which can be written as E of x1 plus x2 plus x3 plus up to x of n. This is what we want to compute. And we have seen that using the rule of linearity of expectation, this can be written as E of x1 plus E of x2 plus E of x3 and so on up to E of xn. All of these terms can be added independently. Now, we also saw that getting a new coupon or getting an old coupon, so whenever this event is can be treated as a Bernoulli trial. Okay, so what is the probability of getting a new coupon? So why it is a Bernoulli trial? Because if you buy a packet of chips, either you will get a new coupon, that is a success, okay, or you will get a coupon that you already have, that means you will get an old coupon, that is a state of failure. So what is the probability of getting the ith new coupon? The probability of getting the ith new coupon. Let us try to find out this probability. So this would be how many new coupons are available. Okay, that is available new coupons after you have collected I minus 1 type of coupons upon total coupons. Okay, upon total coupons, as simple as that. So the probability of getting the ith new coupon is going to be nothing but let's say this probability is equal to n minus, so how many coupons would be available? So suppose you have already collected I minus 1 type of coupons, okay, and total coupons is n. So how many new type of coupons would be available? That would be nothing but n minus I minus 1, okay, upon total coupons, that is n. So that means this probability p is nothing but n minus I plus 1 upon n. And then what is E of xi? Because this is a case of a Bernoulli's trial, okay, so we can say this probability is nothing but 1 by p. The number of packs that you will need to buy to get the ith new coupon is nothing but n upon n minus I plus 1, okay. And what is the value that you want to compute? You want to compute E of x, that is equal to E of x1. So if you put the value of I as 1, what do you get? You get n upon n minus 1 plus 1. So you can clearly see that in order to get the first unique coupon, you only need to buy one pack. Okay, buying one pack will give you the first new coupon. Okay, what about E of x2? So you will add this term. So put the value of I as 2, it becomes n upon n minus 2 plus 1, which is n minus 1. E of x3, that is n upon n minus 2 now, upon so on. To get the nth new coupon, what it would be? You will say, okay, n divided by n minus I, which is n plus 1. So effectively, you can clearly see if you have collected n minus 1 type of coupons, then to get the nth unique coupon, the expected number of packs that you need to buy is equal to n. So that is what this series is. So if you try to simplify this, so what you will get is, you will get, okay, n upon n. So if you take the term n outside, it becomes starting from this thing. So I'm just going to write the terms in this order. It becomes 1 plus 1 by 2 plus 1 by 3 plus up to this term becomes 1 by n. So this is the final result, and this would be your answer. Okay, for any given value of n, you can easily compute this series using a for loop, and you can finally output your answer. So I hope you have understood this problem, and that's all for this video.